Hi everyone, this is Becky, and in this video we're going to talk about periodic table trends, specifically atomic radius and ionization energy. Okay, so as we talked about in class, or as you defined in class yesterday, when we think about the atomic radius, what we're thinking about is the distance from the center of the nucleus to the outermost electron. So essentially, how big is the atom? We're looking at the size of the atom. All right, and so when we looked at the data on Logger Pro, we were looking for patterns. We noticed that the atomic radius tended to decrease as we moved across a period. So if we're looking down here, lithium tended to be the biggest, lithium was the largest, and neon was the smallest. And a radius tended to increase as we went down a group. Right, so lithium is, and so cesium and francium down here are way bigger than lithium, okay? So, and that pattern holds true for the representative elements. These guys in the middle, there's a little bit more variation, but for the most part, size, radius decreases across a period and increases down a group. So let's think about this increasing down a group thing, okay? As we go down a group, so as we go from lithium to sodium, right? The difference between lithium and sodium is that the outermost energy level for lithium is energy level 2, and the outermost energy level for sodium is energy level 3, right? And for potassium, it's energy level 4. So every time we go down a group, what we're doing is we're adding energy levels. And we're adding electrons. So if we're adding energy levels and adding electrons, it makes sense that we're adding layers to the atom, which means that it makes sense that so the radius is going to go up because we're adding layers. That makes sense. That's kind of logical. This part is a little bit more questioning, right? How is it that when we're going across a period and we're adding stuff to the atom, we're adding electrons to the atom, we're adding protons, the radius is getting smaller, okay? And we can explain this using something called shielding. Okay, so as we go across a period, right, we're adding protons. To the nucleus, which means that we're adding positive charge. So if we add positive charge, we're going to increase the amount of force or attractive force that the electrons feel to the nucleus. Think about this like you're standing in front of a fan and we're turning the fan up, right? So the higher the fan, the stronger the fan, the more power we put to the fan, the more of the air you feel. So adding a proton is like increasing the power level of the fan, okay? But we're also adding electrons. But we're adding a specific type of electrons, right? As we go across a period, we're adding valence electrons. So we're adding electrons to the outermost energy level. So if here's my nucleus, here's my valence electrons, right? I'm adding valence electrons. So I'm adding electrons at approximately in the same energy level as the outermost energy level. What I'm not changing are anything that's in here. So I'm not changing the number of inner electrons. So the inner electrons remain constant. So if I'm thinking about the amount of force the electrons on the outside are feeling as, if this is my fan here, and the amount of force is the air that the electrons are feeling, it really doesn't necessarily depend on how many electrons I have out here. It depends on how many electrons I have in here. So we can think about it as these inner electrons are shielding the valence electrons from the force of the nucleus, or they're shielding those electrons from feeling air from the fan, right? And the more inner electrons you have, the more that air will be shielded, or the more the force will be shielded, right? So as we go across a period, we're adding protons to the nucleus. So we're turning up the fan, but we're not changing anything about the number of things that are blocking. So the shielding isn't changing. We're not changing the number of inner electrons, which means that each of these guys on the outside are going to feel more force to the nucleus. The more attractive force they feel, the smaller the radius will be. So as the attractive force increases, those electrons are going to be pulled closer to the nucleus, which means the radius is going to go down. Okay, so as we go across a period, the effective nuclear charge is increasing because we're adding protons to the nucleus. The shielding is constant, so the radius decreases. It's going down as we go across a period, right? As we go down a group, so we're adding protons to the nucleus, but we're also increasing the number of inner electrons, which is going to decrease the effective nuclear charge, or make the effective nuclear charge stay about the same. If this doesn't make any sense, that's okay. We're going to talk about this in detail in class tomorrow, so just let it process. And this might be a video that you want to watch again after class, just to make sure that you've got it, okay? So effective nuclear charge and shielding control the radius of the atom. And we know that the radius is going to increase as we go across, or down a group, and decrease as we go across a period. Property that's very closely related to radius is ionization energy. And so when we talk about the ionization energy, we're only talking about the energy that is required to remove one electron from an atom. So I have an atom and I'm taking away an electron. The energy that's required to do this is the ionization energy. So the ionization energy depends very, very closely on the radius of the atom. Remember from last year, what we talked about with the idea of if I have oppositely charged things, and I'm looking at the force between those oppositely charged things. So how closely those oppositely charged things are attracting. And we say that the force depends on the amount of charge and the distance between them squared. So as the radius increases, the force between the electrons and the nucleus decreases. Which means that it's going to be easier to remove an electron. So the larger the radius, the easier it is to remove an electron. So when we think about that, then the ionization energy turns out to vary exactly opposite in the way that radius does. So the ionization energy is going to increase as we move across a group. Across a period. Which makes sense. The radius is getting smaller, so if the radius is getting smaller, those electrons are held tighter to the nucleus. It's going to require more force and more energy to remove them. And the ionization energy decreases as we go down a group because the radius is increasing. So those electrons are held less tightly to the nucleus, which means it's going to be easier to remove those decreases down a group. I meant to say down a group. If I said across a period, I'm sorry. So the ionization energy is increasing across a period and it's decreasing as we go down a group, exactly opposite to radius, because remember, the smaller the radius, the higher the ionization energy will be, because those electrons are held tighter to the nucleus. Okay, so it turns out that I can remove more than one electron from an atom. It's going to happen successively, though. It doesn't happen together. So for example, if I take the first electron away, right, this is the first ionization energy, and I'm just going to call it IE1 to indicate that it's the removing of the first electron. But it turns out that I can, remove another electron and end up with an ion with a 2+ charge plus an electron. And we call this the ionization energy number 2. And I can keep doing this, right? So I can take my 2+ ion and remove another electron and get a 3+ ion, and so on and so forth. I can keep doing this forever until I run out of electrons in theory, right? A couple of things we should note about successive ionizations. Ionization energy 2, so in this case I've drawn 3, so ionization energy 3 is always going to be greater than ionization energy 2, is always going to be greater than ionization energy 1. Thinking about why this could be, remember that we're taking away a proton, so we have this positively charged ion, taking away an electron. So we have this positively charged ion remaining. By removing that electron, we're decreasing the amount of electron-electron repulsion. Those electrons are going to be held tighter to the nucleus, which means it's going to take successively more and more and more energy to remove them. Okay. At some point, when we start to remove electrons from an atom, right, what we're going to be left with, like you see these are patterns for successive ionizations for the energy in third row elements. All right, so you'll notice here for each one of these that there's a jump. There's a spot in these successive ionization energies. They're always getting bigger, but there's one where it gets all of a sudden way bigger, where we're jumping by an order of magnitude for ionization energy. The ionization energy jumps by an order of magnitude. I want to know why. What's going on here? Right? What's happening when when the successive ionization energy jumps? And how do we know that? And how can we explain why we see that huge jump in ionization energy? Okay. All right. So think about that. Bring your answer to class next time we meet. Also remember that this stuff is hard and it's okay. We're going to go over it in class, and we encourage you after class, if it still doesn't make any sense, watch the video again and then make sure you come in and ask questions.